map pollution loads in watersheds. My name is Ana Paula Generino. I am currently the Water Quality Coordinator under the Water and Socioeconomic Studies Superintendents at ANA Brazil. ANA, for those who don't know, is the National Water and Sanitation Agency of Brazil. This session will provide insights on the partnership between ANA Brazil and the United States Geological Survey, USGS, with a special focus on the development of the R-Sparrow as a collaborative work between the two organizations and its pilot application in the Grande River Basin in Brazil. So before we get started, just a few housekeeping rules. We are using the platform Microsoft Teams today, and this session will be recorded. Unfortunately, there are no simultaneous translation to Portuguese or any other language, so the whole session will be conducted in English. I kindly ask you to keep your cameras closed and your microphones silenced. If you have any questions about the presentations, please type them in the Teams chat, and during the Q&A session, I will ask them to the panelists, okay? So to start things off, I'd like to invite Mrs. Ana Carolina Argolo, who is a director at ANA with a degree in geology and a postgraduate in management and environmental technologies and in environmental geoprocessing. Mrs. Argolo is the current supervisor of the partnership. I now pass the floor to her to give us a brief overview of the work that has been developed so far. So please, Ana Carolina.
Thank you, Ana Paula. Hi to everyone. Thank you, Ana Paula, for introducing me. My name is Ana Carolina Argolo. I'm currently a director in ANA, and I'm going to talk a little bit about the successful partnership between ANA and USGS. The National Water and Sanitation Agency of Brazil is a regulatory agency created in the early 2000s, and our mission is to ensure water security for a sustainable development of Brazil and promote the universalization of sanitation services. We are responsible for, among other things, implementing the National Water Resources Policy, regulating the federal waters in Brazil, managing and coordinating the National Hydrometeorological Network, coordinating the National Dam Safety Policy, maintaining the national system with information of all dams in Brazil, and harmonizing the regulation for water and sanitation services, establishing standards guidelines for the sector. The partnership with USGS started in 2014 alongside the Geological Survey of Brazil, resulting in a 10 years agreement signed in August of 2015 with a scope regarding exchange of knowledge and capacity building in different science areas. After the first 10 years, the MOU will be automatically renewed by another consecutive 5 years. Even though the focus of the collaboration with USGS is capacity building, we have improved some of our procedures and methodologies used at ANA in different areas. One of the most significant results we have had so far is the water quality modeling project. That is the application of the R-Sparrow tool in the Grande River Basin, allowing for an estimation of sources of a total nitrogen in the basin and to evaluate load reduction scenarios. That is the focus of our side event today. The goal of this event is directly related to SDG 6.3, progress on ambient water quality, which aims to improve water quality by 2030, with reducing pollution, eliminating dumping, and minimizing release of hazardous chemicals and materials, having the proportion of the untreated wastewater, substantially increasing recycling and safe reuse globally. And the Sparrow is a tool that quantifies the origin, flux, and state of water quality constituents in the streams and facilitates scenarios of exploration and quantify the effects of management strategies of water quality. The impact of management strategies on constituent loading to streams can also be evaluated using our Sparrow for informed decisions making too. The challenge of collecting data about water quality in Brazil is as huge as the country proportions, but that only highlights the importance of the partnership with USGS, which has helped us tackle this challenge with a great success. So I hope we have a good event today, and thank you so much.
Thank you, Ana Carolina. I am now passing the floor to Mr. Joe Groten, who is a hydrologist at the USGS. Mr. Groten has a master's in water resource science from the University of Minnesota, focused in karst groundwater and surface water interactions in southeastern Minnesota. He is also the current coordinator of the ANA-USGS partnership. Please, Joe, go ahead.
Thank you, Ana Paula, for your kind words. I'm going to spend a little time providing some more background of our partnership before Olivia and Marcelo talk about our Sparrow modeling in Brazil. The USGS has had the great privilege of working with the Brazilian National Water Agency and the Geological Survey of Brazil since 2014. This partnership dates all the way back to the early 1970s, and the USGS has more recently been working under a 10-year Memorandum of Understanding, which was signed in 2015. 3 project annexes have been completed as of 2022, with a 4th project annex currently being planned and developed. Over the course of this partnership, more than 100 USGS personnel and over 1,000 Brazilian scientists from federal, state, and universities have been involved with this program. This partnership has facilitated the exchange of expertise, information, and scientific results in hydrologic data collection and analyses in support of the Brazilian National Hydrometeorological and Water Quality Networks and ANA's overall mission of water resources management. Another part of this exchange includes collaborations with more than 30 personnel from the U.S. Bureau of Reclamation, the U.S. Environmental Protection Agency, and the National Aeronautics and Space Administration, which has included the exchange of expertise in dam safety, water quality, and space hydrology. The primary format of this partnership has included 5 major aspects. 1 being network design and optimization, 2 special webinars, workshops, and trainings, 3 support and systems development, 4 specialized projects, and 5 interpretive studies. During the last 9 years, USGS scientists have had the opportunity to visit monitoring locations in 7 major river basins in Brazil and have visited over 32 different cities, while Brazilian scientists have also made numerous trips across the United States. The cumulative effects of this partnership have been realized with multiple tasks, including but not limited to the quality assurance technical review of Brazilian streamflow datasets, operational improvements, numerous publications, and enhanced modeling abilities, including our Sparrow, which we'll hear more about shortly. And a major outcome of this partnership was that ANA developed and built a hydrologic instrumentation facility called the Instrumentation and Logistics Center, or SIL, after USGS staff hosted ANA scientists at the USGS Hydrologic Instrumentation Facility in 2015. Since ANA now has a SIL available and training provided by the USGS, it has allowed them to quality assure sensors and data loggers, which has helped them make their data collection efforts across Brazil more robust. This multi-country partnership provides an opportunity for a multi-generational advance for Brazil's hydrologic monitoring programs to support citizens of Brazil. In addition, the USGS has had the opportunity to expand its science knowledge related to the world's hydrology and the logistics involved with extreme hydrological conditions, while providing all scientists involved opportunities for scientific growth and personal development. The success of this partnership has led the USGS Office of International Programs to propose this partnerships framework as a model for delivering productive international collaborations with other countries and international entities around this world. Thank you, and I'm now turning it back over to Ana Paula.
Thank you, Joe, for doing this summary regarding our cooperation between ANA and USGS. Now I will turn the time over to our first panelist, Mrs. Olivia Miller. She's a research hydrologist with the USGS at the Utah Water Science Center, and her research focuses on water quality modeling, evaluation of past, present, and future impacts of climate change on hydrology, and regional and continental water availability assessments. Olivia received her PhD and master's in geology from the University of Utah. Please, Olivia, whenever you are ready, you can share your screen.
All right, thank you for that introduction, and Ana Paula, and thank you to everyone joining us today. I will be speaking about a relatively new water quality modeling tool called RSparrow, which was developed in collaboration between the USGS and ANA. This has been an important advancement in making sophisticated water quality modeling techniques open source and available to more people. And it's also led to really substantial improvements in the interactive analysis and decision support for water resources managers. So I think it's kind of taking the sort of complex, researchy feeling water quality modeling and making it a lot more accessible and interactive. One of the big challenges in assessing and managing water resources is that we can often only collect data at a limited number of monitoring sites. That is, we can only measure stream flow or sample water quality at individual points, yet there's a need to understand and manage water resources effectively everywhere, even where we're not monitoring. And so one way to bridge this gap between kind of individual points and entire river networks is through models. So we can sort of take what we learn at these, individual points and scale it up to, a large continental scale understanding if we need that. SPARROW, which stands for Spatially Referenced Regression on Watershed Attributes. It's a model that's been used to quantify the sources and transport of contaminants in watersheds of really widely varying sizes, from catchments to continental scales. SPARROW includes 3 major process components that explain the kind of how stream water quality or quantity can vary in space or time. The first one would be contaminant or water sources, and those could be terrestrial or atmospheric. The second is processes that take those from the land and move them to the stream. And then the third would be things that happen in the stream, so that would be in-stream or reservoir transport and decay. So it's really kind of the whole cycle of how a contaminant moves from the landscape through the stream network. SPARROW is a hybrid statistical and process-based model, and it estimates constituent loads in streams by linking monitoring data in the stream with information on watershed characteristics and constituent sources, and it's all routed through a stream network. The model uses nonlinear least squares regression with mass balance constraints to characterize the spatial relationship between observed water quality, so what you would see at a gauge or monitoring site, and landscape characteristics. So, that would be sources of constituents to streams, and then things that control that delivery of constituents to streams, and then within stream removals in the watershed. And all of that gets routed through a stream network. And once we have that relationship established, then we can predict stream water quality at every reach in the stream network. So what does SPARROW provide? There are a few key questions that SPARROW can be used to answer. One question that comes up is, what is the water quality status and how has it changed with time? And so Sparrow can provide time varying or kind of long-term average yields, loads, and concentrations for every stream reach in your study area. Another question would be how much of the load is from each source. And Sparrow provides source tracking. So you can follow a constituent from where it originates on the landscape all the way through as it travels through the stream network and, to its final destination. Another question is, what are the sources that Sparrow can answer are, what are the sources of a contaminant to a downstream water body? So Sparrow provides predictions of the mass of the total load and the load from individual sources that are delivered to downstream water bodies. So you could say, oh, 20% of the load in this reservoir comes from, some source or a different, either some sort of farming or a wastewater treatment plant. So you get kind of that source specific information as well, which can be helpful for managers, water resource managers. And then lastly, but very importantly, you might be wondering, how good is my model? And Sparrow provides a wide range of methods to assess model fit and uncertainty. Sparrow was originally developed using the statistical software suite called SAS, and an open source version of the Sparrow modeling code is now available because of this partnership between the USGS and ANA, and this is called RSparrow, and it runs in the R programming language. So RSparrow was developed by the USGS in cooperation with ANA and the Brazilian Geological Survey, and RSparrow provides updated and expanded model diagnostic plots and performance metrics. And a key component of RSparrow is this interactive decision support system mapping tool. This allows water managers to evaluate potential effects of hypothetical changes in contaminant sources on stream water quality. RSparrow is also freely available to the growing number of R users. An R Shiny interactive decision support system allows users to map Sparrow model predictions and geographic data by stream reach, catchment, and monitoring site location, and to evaluate the effects of hypothetical changes in contaminant source inputs on downstream water quality loads and concentrations. And so this is just kind of an example of what the R Shiny app looks like. And so I just picked a few of the kind of things that you can work with. And so you can decide, okay, I want an interactive map. I want to look at source change scenarios. There's a variety of different, maps that you can make. I want to look at all reaches. And then here's where you kind of, one of the ways you can define your scenario. So in this example, reduced farm nitrogen fertilizer by 20% everywhere. And I wanted to view the results as a relative change in the load, and that's as a total percent. And so it just, once you have your model, these scenarios are, this took less than 2 seconds to load, and you get these results, and you can say, okay, here in these dark red areas, we got the most reduction in load because of this hypothetical management decision. Here in these blue areas, we didn't see much change. And so that kind of information can help you decide if, some sort of hypothetical management decision is a good solution for meeting your water quality goals or not. Kind of depends on, if you're trying to change water quality here, this solution wouldn't be that helpful here. So that's just kind of an example of, what the R Shiny app looks like and how it works and what you can do with it. Next, I'm going to describe a number of studies demonstrating how Sparrow can inform water resources management. The Gulf of Mexico receives excessive nutrients that leads to overgrowth of algae and eutrophication, and ultimately results in a large hypoxic zone where dissolved oxygen levels are low. And this is really severely impactful on aquatic life. Sparrow nutrient models have been used to predict the flux, yield, and concentration for all the streams that drain to the Gulf of Mexico and to apportion stream loads to major sources and upstream watersheds. So you can see in this map on the left, which shows the total nitrogen yield that actually gets delivered to the Gulf of Mexico. And so the areas in dark green have the highest yields that are delivered to the Gulf of Mexico. And on the right, the bar chart shows the total nitrogen yields from each source by different subbasins. So you can see that in some areas, various sources are more or less important. Sparrow models have been used to provide a framework for prioritizing areas for management actions as well. So this can be done by identifying key areas and sources of pollutants, but it can also be done through scenario analysis. So in this example, Sparrow was used to quantify potential reductions in nitrogen loading to the Chesapeake Bay in response to source and land management decisions. The U.S. Environmental Protection Agency has established a nitrogen regulatory criteria in response to concerns about stream and bay health. And this criteria is expected to result in a 25% reduction in nitrogen loads from 2009 levels. So that's sort of the goal, and that's this red line here. This map on the right shows areas that contribute the greatest total nitrogen loads to the Chesapeake Bay. So the blue are the most, and this is the bay. And the chart on the left shows the predicted percent change in total nitrogen delivered to the bay in response to this scenario is, very extreme, but 100% decrease in total nitrogen fertilizer application. So these blue areas are the 10% of watersheds that contribute the greatest total nitrogen load to the bay. So this scenario exploration analysis found that a smaller reduction of around 25% in just these targeted kind of high yield areas could lead to the required 25% reduction in loads. So, you can kind of see how you can tailor your scenarios to meet your water quality goals. Or you can see, oh, I have this potential solution. Will this actually help us achieve our water quality goals? And you'll hear more about another example of kind of the scenario analysis in Brazil later in this session. Sparrow models have also been used to project potential effects of land use, climate change, and management on water quality and quantity. So the Southwest region of the United States is experiencing a long, sustained, and severe drought. And there's great concern about having enough water to meet demands, both human and ecosystem demands, and what the future of water looks like in a region under a warming climate. In this example, Sparrow streamflow and baseflow models were used to estimate streamflow and baseflow response to future climate change. So here, baseflow means groundwater that flowing into streams, and this contributes in the Colorado River Basin, on average, about half of the water in streams. So the maps on the left here, they show the projections of streamflow change in future years under a moderate on the top and a more extreme climate change scenario on the bottom. So if the 2030s, the 2050s, and the 2080s. And here red indicates a decrease in streamflow and blue indicates an increased streamflow. The maps on the right show projections of future base flow under a warm, wet, a median, or a hot, dry climates, and it's the similar kind of 30-year time periods, 2030s, 2050s, and the 2080s. So again, red indicates a decrease and blue indicates increases. And we don't need to get into all the specific details of the results, but in both studies, you get a sense for how these systems may respond and how that response varies in time and space under different under a range of different climates. And so this information can be used for understanding how much water might be available in the future and sort of long-term water resources planning. Finally, for this last example, Sparrow can be used to understand how water quality has changed over time. Again, staying in the Colorado River Basin, salinity has long been recognized as a problem here for both the United States and Mexico, and it's estimated to cause millions of dollars a year in economic damages to infrastructure and crop production. And there are a number of salinity regulations in the Colorado River, including some established through international treaties with Mexico, for providing water of a certain quality. And so for this reason, salinity management in the region is very important. Our Sparrow models have been used by salinity managers to understand salinity sources, prioritize management areas and activities, and most recently, to understand how loads from various sources, such as irrigated agriculture, have changed with time. So this figure is from a study in progress to quantify the contributions and temporal variability of dissolved solids loads from irrigated lands. And this figure is just showing how loads vary with time for two different sources. So it'd be irrigated lands on two different kinds of rock types. And so this information is really valuable for salinity managers to understand the effects of various management activities and also for how to improve future salinity management. So Sparrow is a really powerful water quality and quantity modeling tool that can be applied to a range of critical problems in water resources management. And through this really wonderful collaboration between the USGS and ANA and CPRM, these tools have been improved and are now more widely available through our Sparrow. And I think really critical to that statement is that they are more widely available to water resources managers, not just scientists. So I just want to thank my colleagues at ANA and the USGS and thank you for your attention this morning.
Thank you, Olivia. This was a great presentation. So thank you very much. Now I would like to pass the floor to my colleague at ANA, Marcelo Souza, who is a water resource and sanitation regulation specialist at the Water Quality Coordination. Marcelo is a biologist with a master's and doctor's degree in ecology and has worked with water quality at ANA for the past 12 years. So please, Marcelo, go ahead.
Hi, Anna.
Hello.
I'll share my screen here. Can you see that?
Yes, it's perfect.
Thank you. Just set my time and good morning. It's a rainy day here in Brasilia. I work with Anna with water quality at the Brazilian National Water and Sanitation Agency, the ANA, and it's a privilege um, to present this work done in a cooperation with the USGS and the Brazilian Geological Survey. I have divided my presentation into 4 parts. Firstly, I will talk about the context in which the work was developed. And after that, I will mention some deliveries made in this contest. And the third part is about the study we carried out here, applying Sparrow in a Brazilian watershed and its results. And I will finish with some brief conclusions about the work. Yeah, first I would like to speak briefly about the Brazilian water resources policy. And among other objectives here, our water law aims to ensure access for present and future generations to water of a quality compatible with its various uses, And to achieve this goal and others, our policy provides for the implementation of 5 different management instruments. We have the water resources plans, and we have another instrument related to regulation, granting the permits for the water users. It's about water allocation, charging for the use of water resources, and this is about financing actions, management actions at the basin level. We have our water resources information system and the water bodies classification system based on water uses and water quality standards. The water bodies classification system is a planning instrument specifically designed for the management of water quality in rivers and lakes, all kind of water bodies. And it is based on quality classes defined by a set of physical, chemical, and biological parameters. And such classes of quality are assigned to reaches or water bodies according to the uses of their waters. Once the quality classes of a river or lake are defined, they become goals to be achieved through management actions. The class definition is a participatory process that includes many studies and results in a classification proposal and also in an implementation program. Um, The use of large domain hydrological models is very useful for the elaboration of these classification proposals and also for the planning of actions aimed at controlling the water pollution at the basin level. And because of that, implementing modeling and improving our water quality studies has been quite challenging for us over this last decade. And as Ana Carolina said before, ANA-USGS and also the Brazilian Geological Survey signed a Memorandum of Understanding, the MOU, that includes water quality interpretive studies. And in this context, we visit the USGS offices, I think it was in 2016, to prospect tools and methodologies with some potential to help us in our everyday job. And among the various studies they presented to us, the Sparrow modeling tool seemed to be the most attractive option because of its ability to quantify and identify the main significant sources of pollution in large watersheds. Um, and now I will mention some important deliveries of this that happened in this contest. After the technical visit, we started a series of webinars with the USGS team and also with the Brazilian Geological Survey uh, about water quality modeling and water quality studies. And after some webinars, we decided that it would be good to start a pilot study using Sparrow to put in practice all the things that we were discussing at the time. And this pilot study was published in the journal Water in 2020, and 2 years later, we also published a booklet in Portuguese, and also uh, another important delivery was this open source version of the original Sparrow. The original Sparrow was designed to work with SAS, which is a paid software, kind of expensive, and it could be an obstacle for us to acquire that software at the time. And we asked USGS to continue an old project of having um, open source version. The R Sparrow is now available on GitHub for everyone. And a key component of this R Sparrow modeling tool is an interactive decision support system that allows managers to evaluate the potential effects of hypothetical changes in contaminant sources on the stream water quality. Now I will return to our pilot study. Well, we decided to study the Grande River Basin because there were lots of fresh data used for the elaboration of the integrated water resources plan of the basin at that time. And uh, and also because the basin has interesting characteristics for us to apply the Sparrow there. In that basin, nitrogen is a very critical water quality parameter because of the risk of eutrophication in the numerous and large reservoirs of the region. There are a lot of man-made lakes used for hydropower production. And our goals were to test the potential of Sparrow to identify relevant sources and quantify the spatial variability in mean annual nitrogen loads in all streams across the basin. And we wanted to test the hypothetical load reduction scenarios and check the positive impacts on the stream water quality. Many sources were tested for the potential inclusion in the final model. This is the procedure when you're working with Sparrow. And we included agricultural land area sources and urban land area, population, and uh, point source inputs from wastewater treatment plants. Air temperature and precipitation were also tested for inclusion in the model as landscape transport characteristics. And the final configuration included four source variables: wastewater treatment plants as a point source, uh, sugarcane cropland, urban and pasture land as non-point source. The main result is that the model estimates that of the 20,000 tons of total nitrogen delivered every year to the watershed outlet, 11% originated from pasture land, and 28% from urban landscapes, 32% from the sugarcane cropland, and 30% from the wastewater treatment plants. It's interesting that 11% of the total load came from pasture land, and pasture land makes up only 2% of the total area that we studied. Nearly 1/3 of the total nitrogen load being delivered to the outlet was from the wastewater treatment plants. It's a lot, and loads of nitrogen from this load could be reduced by improving levels of wastewater treatment And the source reduction scenarios we tested to assess the potential impact of such hypothetical actions showed that relative to the baseline conditions, the nitrogen loading at the outlet of the subbasins, the two subbasins, decreased by 6% when the 20% reduction in wastewater point source inputs, 12% for the 40% reduction scenario, 18% for the 60% reduction in the loads from the wastewater treatment plants, and 24% for the 80% source reduction scenario. We did the same thing with the nitrogen that came from the urban areas, and relative to the baseline conditions, management actions, hypothetical management actions aiming at treating currently untreated urban runoff could decrease nitrogen loading at the outlet by 6% for the 20% reduction in loading per unit area from the diffuse urban land sources, 11% for the 40% reduction scenario, 17% for the 60% reduction scenario, and 12.2 for the 80% source reduction scenario. And to finish my presentation, some general conclusions. First of all, I can say that it has been very interesting for us to know about the non-point sources of nitrogen. In many cases, it has been a mystery for us, the non-point sources, and playing with the scenarios are very helpful to inform management efforts aimed at controlling the water pollution. And it's very helpful also to support the water bodies classification instrument, the elaboration of the classification proposal. And the other positive thing is that we were able to develop the model using the available information that we have at the agency, and also the historical data from water quality and quantity monitoring network. And we believe that our models can support the strategic development of these monitoring networks in the future. And finally, the open source nature of our Sparrow provides a great opportunities to explore other basins, and also to work with other water contaminants, for example, phosphorus and sediments, and BOD, depending on the problem that you have in your watershed. You can explore new critical parameters. And just to finish, I'd like to send a big big hug to this technical team. There are more people that are not in this list, but here we have great friends, excellent technicians that helped us a lot, and they keep helping us. And that's all for today. Thanks a lot. This is my email. You can email me if you need some help, if you need to know something more about Sparrow, the application that and our study in Brazil. Okay, thanks a lot.
Thank you, Marcelo. This was a great presentation. So thank you very much.
Thank you.
I would like to ask those who are who joined us here today for this session to please type your questions here in the chat. Don't be shy. There's no wrong questions, okay? While we have no questions, I will just start asking for Marcelo and Olivia to please talk a little bit more about other water quality parameters that can be used in Sparrow. For example, does every water quality parameter work to be used in Sparrow, or there are some preference? Could you talk a little bit more about this?
Sure, I can talk about that first,
Thank
and then Marcelo might have some ideas too. One of the really important things when you're selecting a water quality parameter to make a model of is the amount of data available for it. And so you need quite a bit of monitoring data, over a large, your whole modeling domain, kind of over representative areas of your modeling domain. And so the model will be better for a constituent that you have more data for. So if you don't have a lot of data on certain constituents, then your model probably won't be very good. So I think that's sort of the guiding principle of deciding if a constituent is an appropriate one for a Sparrow model. And then beyond that, I would say, like salinity is a very easy one to model because we assume that it's non-reactive, it's a conservative tracer, and so it's sort of just tracking mass. It's, gets a little bit harder to do things that have, maybe more unknowns about the processes that might happen as they move through a watershed. But things like nutrients, we've had a lot of success. So nitrogen and phosphorus, we've had a lot of success with those models. Things like, salinity, sediment, and then the water quantity models have been pretty successful as well. So the stream flow and the base flow. I don't know, Marcel, if you want to add anything to that.
Olivia. Yeah.
Yes, it works better when the constituent has a good relationship with the stream flow also. And this is kind of rule for Sparrow. And I think it's, as Olivia said, everything that we needed to hear about that.
Okay, thank you. So we don't have any questions here in the chat. Does anyone that is here in today's session want to ask something for our panelists? Please say now. If no, I will leave their email addresses here in our chat, and you can ask questions for them later, okay? I will also put here the links for the two publications that Marcelo mentioned. One is only in Portuguese, the ANA's publication, and the other is an article. So if we have no other questions, I would like to thank everyone who is here for joining us and watching our side event today. And I also would like to highlight the importance of this partnership, of this cooperation between ANA and USGS. It's been a very fruitful partnership. We were able to develop tools such as our Sparrow, and at the water quality coordination, we were also able to leverage our water quality data to make better water quality reports. So thank you once again for joining us, and hope you have a wonderful time following the UN Water Conference 2023 in the following days. Thank you. See you guys.
Thanks a lot. See you soon.
Thank you.